Okay. We talked about water flow a little bit. I'd say that's most of the things I want you to take from the physicist aspect, of the physicist point of view of soil, right? Particle size. Particle size implies pore space, all right? Implies water flow, implies water retention, all right? Let's take a look on the chemist point of view of soil, all right? The most common thing we say about the chemistry of soil is nutrients, right? We talk about nutrients. Many people they always think they need to add more. Agronomists will always advise farmers to add more fertilizer and more fertilizer into the soil. If you take a handful of this soil and you dissolve it in a strong acid, right, where all the mineral particles, everything in this soil becomes liquid, right? And we take a sample of this liquid, and we test for nutrients, for what minerals are making up this soil, right? You can look it up on Google. You'll find lots of random tables with like iron, aluminum, calcium, magnesium. All the minerals in the periodic table will be there, and in high numbers, very high numbers. Right? Lots of iron, lots of calcium, lots of nitrogen, all the nutrients will be there in very high concentration. The problem is they are locked into the mineral structure. For them to get released into a plant available form can take centuries, can take millennia, right? Can take many times, many years. That I want to talk about nutrients and nutrient pools in the soil. When I say pools, I'm meaning sources for nutrients in the soil. So that will be our first pool, all right? It's the biggest, right? There is the most nutrients in this mineral structure, right? But it's the least available. It takes the longest time to go into solution. Another pool of nutrients that is highly available for plants is the soil solution. Right, is the water between the pores that always have in them some salts. Right, those are the minerals. Those are the nutrients. Okay, these are the most available nutrients for plants, but the least amount. This is the smallest pool of nutrients. Right. The third pool of nutrients is kind of like the intermediate one. Right, it's attached. It's not part of the innate mineral structure of the particle, is just sit around the surfaces. It's attached to the surfaces of the particles, but not so strong. Right? It will take days, maybe weeks, for these nutrients to get released. A plant taking up some nutrients from the soil solution, within a few hours, a few days, maybe a few weeks, the nutrients that are attached weakly on the surfaces of the particles will get released into solution. All right?
Question.
Yeah.
So the solution, the water that has nutrients, is that naturally in the water, or the water's leaching it out of the soil?
Whenever rain drops, rain, we can think about rain as water lacking any minerals, any salts, right? Not like our tap water. Our tap water has some minerals in it. Once a raindrop touches mineral ground, it starts to dissolve a little bit of this mineral, just a tiny bit of it, all right? And it always has some nutrient. There is never distilled water in the soil. We can never find distilled water in the soil, right? So the solution is the highly available. The exchangeable is our storage, all right? And the mineral is the long storage, way longer for our grandkids, right? Like this is for way later. pH is my next point. I will get to it in a minute. Another thing, okay, the exchangeable pool right? Within our particle size distribution, within our texture, the smaller the particle,
Yeah.
the more it's contribute to the exchangeable pool, right? Think about it. We reach, if we say we have 30% clay, 30% silt, 30% sand in the soil, right? Just generic soil. If you think about the amount of particles, right? We'll have way more clay particles, right? In this 30%, way more particles. And then if you think about the surface area, the surface that's outside the particle, right? Compared to its size, it means we have way more surface area. And in chemistry, surface area is the chemically active area when all the chemical processes are happening, all right? And on these surfaces are the exchangeable pools of nutrients, all right? So the clay range of particles contribute the most to the exchangeable pools. Another thing that can contribute to exchangeable pool of nutrients is organic matter, and we'll touch it in a minute. pH. Right. I don't think soil pH is a very important parameter to check. Most soils ranges between 6 and 7.5. All right. Outside these ranges, we talked about a little bit before. Outside these ranges, if your soil is say 5.5 or 7 or 8, right, then it's going to start to select for certain plants. Right? Certain plants won't grow in this kind of soil. Certain plants will.
And what do you call that type of soil that's 7 and 8? Acidic or alkaline?
All right, 8 will be alkaline soil. 5.5 will be acidic soil. Conifers drop the pH, makes the soil more acidic. And start, if you see under conifers, under redwoods, under pines, you see certain communities of plants going on because the soil is getting more and more acidic, right? To change soil pH from outside this range of 6 to 7.5 to go back, it's hard. That's not easy. That takes time. So that's why I'm saying pH is not like the biggest concern you have in the soil. Plants, I wish I'd done that. Anyway, plants, imagine the root system, right? We got the taproot going down, all kinds of roots are branching off, okay? The root system fill up space, three-dimensional space under the soil. This root on this side can alter the pH around it to have the nutrients it needs available. The root on that side can alter the pH around it to a whole different pH level to extract other nutrients. And so the plants can do it during the day. Can change the pH of the rhizosphere, of the soil, very close to the roots to get the nutrients it needs. It can change the pH during the day. You can check one the morning, you can change it in the evening, you find a different pH. All right? So that's why trying to control for pH is hard. If you're talking about container planting, that's a whole different story. Okay? Remember, because soil is so big, there is so much of it, the volume of soil is so big, it's hard to alter chemistry and physics of the soil. All right? Let's see. Organic matter in the soil. We talked about the mineral particles. There is organic particles in the soil as well. Most soil ranges between 0 and 10% organic matter. If you test your soil for a chemical test, they will have a line of organic matter, OM percentage, and a number next to it. Most of your soil will be, I would think, between 2, 3, 4% organic matter, okay? Keep in mind 3%. That's our threshold. We talk about it a little bit later, okay?
But would you define organic? Are we talking about like dead leaves?
Organic
or
material
bugs?
is carbon substance, carbon-based substances. So yeah, it's decay organic material usually. That's the source of the organic matter. Okay, dead stuff, right? Dead leaf, dead animals, all kinds. So that will constitute the organic material. Some of the organic material is solid particles. All right. Some of the organic material will dissolve into the solution, into the water of the soil. Right. I haven't talked about my little jar here, but you can see there is some stuff floating on top of it. So I just took soil, a bunch of soil, put it in a jar, added some water, and shake it. All right, we're gonna shake it for a few seconds and just let it rest. Whatever floating up there, that's the solid organic material. All right. Once all the small particles will settle down, and that might take hours to days to weeks, then I will end up with a solution, the soil solution, just the water, right? If the water is clear, transparent, it means I barely have any organic matter dissolved in this water. A good soil with organic material will leave a brown, transparent but brown water. All right. So we already got two things we can learn about this very simple test, right? And I'll go back to it later. Organic material in the soil usually is very big organic molecules, that huge organic molecules, very chemically active, right? So it adds to our exchangeable pool of nutrients that we talked about before. So same as clay. It will add more and more sites for nutrients to get hold on their surfaces and be released whenever needed. All right? This is available nutrients for plants. Just take a little bit of time. But not as much as the mineral pool we talked about. Another thing organic matter help us is to form these clumps. All right? Because it's chemically active, it can interact with the different particles, and works like a glue. Almost, okay, so it can hold a few clay particles with it. It can attach it to some sand particles or silt particles and create our little clump, our little aggregate, right? Okay, two more things about organic matter in the soil. So it helps produce these clumps, these aggregates, okay? Another feature of organic material, it can absorb water, a lot of water, usually twice its weight, all right? So it adds to our water retention capacity, it adds to our pore space, to our water storage by building the clumps and by holding on water, all right? So more organic material in the soil, the more water retention we have, right? That's very important.